All right, 3, 2, 1. Someone new. The next 2 questions. Someone new. Walk about. Walk about.
Okay,
You should have got to by the
I know.
I was really confused the whole time. I thought I looked at the right color.
Make sure you do that for me. By next week. All right, loves. Last question. Find something new. Do number, if you can, do number 6 and 7. If you haven't done 6 already, okay? So now let's get the calculation side. 6 and 7. Someone new.
Okay.
I don't want to get up. I don't want to get up. All right, Ian, go back to your seats for me. All right, so somebody take really good notes for Cassie, Megan, and Niall. Got it? I'm going to be here too, but be a good friend or something. All right. Okay, so as you can tell, thermochemistry has a lot of vocabulary terms, and the vocabulary terms mean very specific things, like the vocabulary terms mean that. But the idea is that you should be able to relate them to an equation or to a calculation that we'll be utilizing today, okay? So we're doing 2 things today. We're going to go through work and energy first. We're going to pause. We're going to work on problem set. We're going to do heat transfer and calorimetry, pause, work on problem set, okay? So work with me. I'll be repeating myself probably 3 times throughout the day with some of the vocabulary terms specifically. And so to keep your attention, I'm going to pass around my bag. This is not normal trick-or-treating. I'm passing candy out to you. Pouring my candy to you. You're stealing candy from me, okay? So we're going to pass that candy around to keep you enthusiastic and excited. All right, so we will be mentioning basically all of these today. How did you guys feel with these? I see a lot of okay. So re-explaining it is a little difficult until you really wrap your head around it, okay? So we'll work through this as we go. All right, so as we're going, I would be taking notes, and I'm, of course, encouraging you to draw pictures and help you with your calculations and so forth. I'll be adding a couple of extra things to the board. If you printed, I saw most of your packets or your reading. If you just annotated yours, I didn't see that because I wasn't looking. I was looking for like the front page of the packet. So if you guys can have your homework on your desk still, I got to see a couple of people's provided things. So here we go. The idea that we now are basically transitioning from gases to all states of matter, okay, solids, liquids, and gases, means that we can talk about energy in solid phase, the liquid phase, and the gaseous phase. So which of those three states of matter is the highest energy? Obviously, right? They're bouncing off the walls. Who's the lowest state of energy? Solids. But between the three phases of matter, and then even up to plasma, if we want to talk about that, there's an energy difference between them. But these, the transition between solid and liquid and gas is a chemical change or a physical change? Physical change, because what is not changing? The chemical composition, just the appearance of them will change, okay? All right, so as I go from solid, liquid to gas, tell me what's happening to the motion of the particles. The molecules themselves are what? They're moving faster. Let's do this together, okay? Put one finger up. Okay, so translating from side to side, rotating, and then there's one more. Oh, vibrating. Okay, so those are the three forms of motion: translating, rotating, and then vibrating. And that's what the gas particles are doing quite a lot of. So these have the highest kinetic energy. What's kinetic energy mean? Energy of motion, which is directly proportional to temperature in Kelvin. So solids have the lowest kinetic energy, and liquids, of course, have the mediocre form of kinetic energy. So as I go from solid to gas, is that an endothermic process or an exothermic process? So think about it. I went from low energy to high energy. What did I do to the system? I put in energy. So what kind of process is that? Endothermic. So in the direction that I have the arrows drawn, this is an endothermic process. And I'm really specifically using the word process because it's not technically a reaction, because reaction is a term utilized for what? Which types of changes? Chemical changes, where I'm really talking about a physical process, not a physical reaction. So in the opposite direction, if I'm cooling something down from gas to liquid and space changing back, this is the what direction? Exothermic process. So our particles are cooling down by releasing energy, but in terms of releasing energy, I'm not really specific there. I'm not saying kinetic energy, potential energy. It's energy as a whole until we can really whittle down to the facts. Okay, in your reading, you saw a big emphasis on surroundings and system, right? What is the system, just in general? Our focus. So if we were doing an experiment, it would be the reaction, the beaker we're holding the reaction in, and like the thermometer we're using to measure energy differences. The surroundings, sometimes it's our entire system because we do have to include the chemicals. Occasionally it's also equipment, because our equipment can absorb energy. And if it absorbs energy, we have to account for that as well, especially if we have the opportunity to, we will. So I'll say sometimes it's equipment. Sometimes, if we can separate the equipment from the contents of the beaker, something like the chemicals, then we will keep this as its own system, and we'll include everything else around the chemicals as the surroundings. It just depends on how good our data collection techniques are. Okay? So there is always an exchange of energy between system and surroundings. Who has something either warm or cold with them right now? A couple of you guys? Okay. So I'm holding my warm chai tea. It's good for the soul, okay? And I can feel it's warm. Well, how am I feeling this after it's warm? Okay, but what would you consider my hand to be? Warmer or colder than this? Okay, so why is my hand not sending energy to my tea? Okay, so it always goes from what to what? High energy or high thermal energy, high heat to lower heat. So until when? Does it just keep on warming my hand up and cooling this down? To what? What's the word that means heat equilibrium? So it starts with a T. Say again? Thermal equilibrium will be achieved. Is that what you said? Okay. So thermal equilibrium would be achieved when both the system and the surroundings are at the same temperature. And that's when your beverage or whatever you may have stops changing temperature, because the system and the surroundings are not the same temperature. Okay. Okay, so these are your definitions. Does anybody else need candy? You can just put it on the floor, I'll get it. I'll pass it around again in a minute. Okay. All right, so these are your definitions, and these definitions are like the key to understanding our terminology so we can communicate together. So I'm going to take a minute and let you read and remember, or read and write. Because some of this is on your reading you did, if you wanted to highlight or star the terms on your first 2 pages of your reading, you can do that as well. Maybe you're just writing those terms so that you can reference them as you go. Alright, so the one I have in blue up here, energy in general. Generally we call it energy, but it can also be called internal energy, which I have at the bottom of the slide. I'll scroll down to that in a second. It's not just thermal energy. It's also, as a collective entity, the ability to do work, which we will then today be able to calculate work. So work is just movement, really one way or another. Okay, so I can have movement in, like compressing something, or I can have movement out, like expanding something. Well, if I say compression and expansion, what state of matter do you think I'm kind of referring to? What state of matter can I compress and expand? Gases, right? So I'm going to deal with gases more in chemistry, with energy, but you can also deal with like distance travel would be work. That would be more of a physics kind of entity, because we're not talking about like chemicals moving distances. We're talking about them moving their volume or compressing or expanding their volumes. So it's the collective work and energy together, work and heat together. W plus Q. Okay. All of these terms here are just making sure that we're clear on what we're talking about when I say temperature. Temperature is not heat. Heat is not temperature. Kinetic energy represents how particles move, but it's still itself is not temperature, nor is it heat. But they're all related in a direct proportionality. So kinetic energy, energy of motion, we already knew that. And then what equation comes to mind when I talk about mass and velocity? 1/2 mv squared, right? So we know that there's a relationship between the kinetic energy of a particle and its mass and velocity. Potential energy in everyday life, so everybody maybe take a second, hold your pencil like this. Your pencil or pen has potential to do work. What can it do? It can fall a certain distance, right? It has the potential to do that because it has, because of the difference in gravity from here to here. So they have the potential to do work. But we're not talking about distances being traveled in chemistry. That's more of a physics thing. So we're talking about the potential energy within chemicals, which is stored as chemical energy in bonds. So potential energy is generally stored in bonds. So the ability to get the energy out of those bonds means that we're talking about chemical reactions. Whereas you guys did read this, I'm not sure if you remember it, but when you form a bond, you either release or you absorb energy. When you break a bond, you either form or release energy. So it's one or the other, it's not both. Can anybody tell me what happens when you break a bond? Say again? Alright, everybody do Genie. Okay. Alright, turn. So everybody's doing this, right? Okay. Okay, so come on up. So you are a bond. Your elbows are atoms, you are a bond. And I'm going to break her bond, okay? Yeah! Yeah, karate chopper. What did I do? Did I take energy from her, or did I put energy into that? I put energy into it, right? You will never forget the karate chop. I will never remind you that. So it took energy to break your bond, so this is an endothermic process. But then when you come back to peace, when you form your bond, is this an endothermic or exothermic process? Oh, you're releasing energy. So as you form a bond, it's actually storing energy, which is well, no, it's storing energy, but as you form a bond, it's coming to a more stable arrangement of atoms. That's going to be releasing energy. And as you break a bond, it requires energy to do that. Think karate chop, and that will remind you of endo. We'll reference that a lot throughout this week. Okay, we know the temperature. We know it's directly proportional to Kelvin temperature. Kinetic energy is directly proportional to Kelvin temperature. That's fish directionality or proportionality. And then heat is a sum of all what? Kinetic energy. So that gives us the idea that heat and temperature are related, which we will come to find out. What equation has heat and temperature in it? Anybody? Q equals mc delta T, right? Or mcat, right? So there's an equation that's going to pull these two definitions together. We are talking about transferred energy though. So heat, we can calculate internal heat, like of my coffee, I could definitely calculate the internal heat. But a lot of times I'm looking at the transfer of energy or the transfer of heat, so I'll have two objects involved. Remember, joules is our energy unit, and the energy unit we use for work, work and heat, because those are both of my energy entities. And then here's your big boy equation. To internal energy, which you guys saw on the third, fourth page of your reading. Internal energy is the combination of work and heat. But it is, the definition of it is just all the molecular kinetic energy and potential energy. But potential energy is so difficult to calculate. It really is. It's not, there's no simple calculation for internal or for potential energy. So a lot of times we look at the change from beginning to end. So that's why we have a big delta here. Delta means change. So a lot of times we're looking at the change because I can't definitely just define what the potential energy's number is because I don't have a calculation for that. And then we will always be able to calculate Q because generally in our reactions we'll be given information about like the mass of a substance, the temperature change that substance underwent, and some other variables. But I don't always, I'm not always able to calculate work because work is based on, does anybody remember the equation for work? It was in your reading? W equals negative P delta V. Okay, so in every situation we deal with, we're not going to have a volume change. We're just not. So if I don't have a volume change, what does work equal? If volume change is 0, times negative P, doesn't matter what the pressure is, the work will be 0. So I sometimes won't have work involved because I don't have a volume change. But you will usually always have Q, which will then give us the ability to calculate energy. Okay? But if I have both conditions given, you can certainly add them together. Give me a thumbs up when you're good here. All right, so I'm going to elaborate on some of the main concepts, and then we'll do some calculations too. Okay? You guys are good. Just tell me when you guys need a break, okay? Okay, so who saw these in honors hymn? These potential energy diagrams. Okay, this one says free energy. You can relate it to different forms of energy. Free energy is extra energy, but this is just potential energy. So turn and talk to the person next to you. I want you guys to think about this. Is this an endothermic process or an exothermic process that this curve is representing? Just turn and talk to the person next to you. Okay, that was probably enough time. Any loud and proud answer? 3, 2, 1, go. I heard both. Louder and prouder if you're really confident. Exo is what I heard. Okay, thank you. So here's what you're thinking about. Listen. You have reactants with set amount of energy, right? The products that are produced, this is P down here, products, they have more or less energy than the reactants. Less. Okay, so reactants had a lot of energy, products don't have as much energy. What happened? So over the reaction process, energy was, I want to say released, because energy is never lost because of the law of thermodynamics. First law of thermodynamics, energy is conserved. Okay, so this amount of energy was released. And if I had values, let's say this was like 100 kilojoules of potential energy, and this down here was 20 kilojoules potential energy, you guys could tell me how much energy was released. How much? So this would be a delta H, meaning energy of reaction, or heat of reaction, of negative 80 kilojoules, because that's the amount of energy released. So why am I putting negative? So I'm releasing energy, right? I won't say losing necessarily, but I'm releasing energy, so therefore it's an exothermic process. So how would the curve look at those endos? Draw it in the air for me. So I saw like a little pump up and then kind of stay elevated. Okay, good. So we're going to talk about that in a second. This is a little bit of a different enthalpy diagram. It's a little bit more difficult to read, but what you're seeing here is that the two reactants, whenever they react to form liquid water, there's a huge release, negative 286 kilojoules of energy that's released. But it actually takes 2 steps to do. The first step is H2 gas plus O2, or half O2 gas, goes down to form gaseous water, and then the gaseous water undergoes what to go to liquid water? What's this process from gas to liquid? Say again? Condensation. Ooh, thought I lost you there. Okay, so this is a condensation process, but it takes 2 steps. But overall, I see that the entire reaction has a negative delta H value, which tells me that it's exothermic. Okay. All right, and then, oh, this is what I specifically want to reference here. So the way we always reference state functions, anybody want to tell me what a state function is? Is that the one question that was like, okay. Marcus?
I think it's a function used to describe a change in state.
Not quite. State function. State, you're thinking phase of matter, right? So state function is the process of recognizing that there's a whole lot of stuff that could happen in the middle here. Like this is representing an overall change, which is the only thing I really care about. I care about where I started and where I ended. I don't care if this took 15 steps to happen between here. It could have taken 1 step or it could have taken 15 steps. We don't care about what's happening in between. We only care about the beginning and end, which is why we always reference the reactants and the products, and then gives us the opportunity to really specifically look at energy of products minus the energy of reactants, and this will tell us if the value is plus or minus, meaning endothermic or exothermic. So if you get a positive difference, it's endothermic. If you get a negative difference, it's exothermic. So this is H products minus H of reactants, or energy of products minus energy of reactants. We will reference that a lot as well. Okay. Okay, so on this next curve, tell me endo or exo? Endo. Okay, so do your H products minus H reactants. You have values here. What's your H of products? H products minus H of reactants. H products you guys said was what? Approximately 300 kilojoules. I'm saying this is kilojoules. And what's the reactants? And so this overall process is what? What's this mean though? So, okay, it's a positive value, which I'm hearing is endothermic. What else does it mean? Another word for gain? Absorb. Okay, so this whole process, the reactants absorbed 200 kilojoules of energy as they form those products. Thumbs up? Easy so far? Just the terminology will kind of hit us hard. Okay. All right, so we've referenced this already, but the value or the variable we give to heat is what? Q, okay? We will start to reference Q as heat, and sometimes we'll reference it as enthalpy, which is signaled or signified as delta H. They are not always exactly the same thing, but we will tend to say that they are equivalent because of the conditions that we're describing the reaction. So enthalpy is what we'll speak of more like tomorrow. Heat is really what we're focusing on today. And notice that I'm mentioning in my definitions of endo and exo, system and surroundings, right? So I'm specifically, the perspective that we generally come from is not the surroundings, but it's the system. So be one with the system. And think about how the energy is being exchanged with the surroundings, but you are specifically taking the perspective of the system. Notice that I have heat and work here, which these combine together to make what? Say again? Energy or total energy or internal energy, delta E. So that's we're speaking of those together here. What are they both measured in? What unit? I have it written up here. Joules, right? That is the energy unit you have to use, or kilojoules, but we have joules here and joules here. But today we're going to learn how work, what's work's equation again? Negative P delta V, like that's pressure and volume. That doesn't equal joule. We'll learn how to convert that today as well. Okay. So if energy is leaving the system, which another word for that is released, then we'll say that the process, or the from the system's perspective, the process is exothermic. And if energy or heat is entering the system, which another word for that is what? Absorbing energy. Then that process is or endothermic as it relates to the system itself. For work, which is W, we talk about the compression or expansion of a system. So let's say this little box is a certain volume. If the work is done on the surroundings, then the system is losing its energy. Because if you were in a box and you had to push the surroundings and the box away from you, you're really exerting a lot of energy. So if the system is inside of here and you're pushing on your container, you're doing work on your surroundings, which is around you, but you yourself has lost some amount of energy, which is why we denote work with reference to the system as negative, because it lost, it used energy to do work on the surroundings. Does this make sense? It's a little, you have to think about it as you go. And then opposite, if work is done on the system, let's say the surrounding is compressing and it's squishing our system in, it actually gives the system more energy to do work with, or it gives it more potential energy for that, for some cases. So if work's being done on the system has gained energy, and so therefore we write as a positive work, or positive W. So do you see how you have to think about it, just determine the positive and negative? Don't just willy-nilly assign values. Give me a thumbs up on it. So because we're talking chemistry, generally we're talking about gases, because gases are what we'll have P and V for, so pressure and volume. And that's going to be, I think, next year. Okay. Almost next. All right. So this is kind of bringing everything together. Just take a minute and read that first, because I've kind of described these already. You need to write down a definition. And there you go. So state function, there it is. We don't care about what happens in the middle. We care about the beginning and end. So we said that it's independent of the pathway taken. So if, like I said, the pathway could be 1 step or 15 steps, but we don't really care about what's happening in between. We look at the net change, which is why we put a delta on energy. And so anytime you have a delta, like for example, delta energy or change in energy, you're referencing E final, so energy final, and you're subtracting E initial. And that will be every single time we write a delta. Where else do we write delta? Don't look at the view. Where else do we write delta in thermochem? In what? MCAT, so it's the delta with? Delta T, right? So delta T will be T final minus T initial. So it's very specific to that system. And that's where how we also indicate delta H. When I wrote delta H, it was H what? H what? Reactants or products? Products, which is final, right? Minus H of reactants, which is our initial. It's always final minus initial. Okay. So we don't have Q and W as deltas because they're not technically a state function. There's a very specific change that's happening there, and it's not like there's no mechanism and nature to it. It's one step. And then, like I said earlier, expansion and compression. Expansion means we're doing work on the what? Surrounding, so the work is positive or negative? Negative, and if something's compressing our system, we're doing work on the system, so the work is positive, okay? And then this is your work equation, negative P delta V. It does relate to force, so does anybody know well, here it is right here. Does anybody know the definition of pressure? Force applied per area, okay? So rearrange this equation and solve for F. So F, just drop on my desk here. Pressure, or force is equal to pressure times what? Area. Okay, so if I'm telling you that work is also like in physics terms, Work is force by distance, so force applied per distance. Plug in F value here, so work is equal to what? Pressure times area times distance. And what is area times distance? Which, instead of saying distance, I could easily say height, like height of a cylinder. Volume, so area times height or area times distance is just volume, but we specifically look at the change in volume because overall it's a process where we start with one volume, we end up with another volume, so that's why we have delta. And then how do we get that negative in there? Anybody? It's always about the perspective of the system. Okay, so the perspective of the system actually means that if the volume is decreasing, let's say I go from 100 liters, go from 100 liters to 80 liters. How do I subtract volume? If I'm going from 100 liters to 80 liters. 80 minus 100, which is going to give us negative 20. And so the volume change being negative to the perspective of the system, doing work on the system. So I can't have a negative work because that would be wrong. That would be me doing work on the surroundings. So I put a negative in the front to offset my volume changes so that it does relate to the system's perspective. Okay? All right, so let's do one more thing and then we'll do calculations. Okay, this is just a definition of the first law of thermodynamics. I think we've read this like 3 times in our reading, but I'll tell you my favorite thing is this light. It says, turn off the lights, conserve energy. It's always conserved, man. You know what I'm telling you? Like, don't turn off the lights and then conserve it. We're talking about first law of thermodynamics is always conserve. We're not going to lose energy. We're not going to gain or create energy. Energy is conserved, no matter if you turn the lights off or not. It's just saving electricity. Okay? So the energy that the system has and a change in that energy is just delivered or given to the surroundings or vice versa. So you'll notice that one of them is positive and one is negative because the system, the way I've written it here anyway, the system has the endo side of things and the surroundings has the exo side of things. So who's giving energy to who? Who's giving energy to who? Surroundings is losing the energy to the system. So if I had, who's got something like icy? We have a bottle of water here. Borrow this, okay? So it's a cold bottle of water. My hand is the surroundings. My hand touches the cold bottle of water. What am I going to start to do to this bottle of water? Warm it up, right? So the temperature is increasing. Is that an endothermic or an exothermic process? Okay. Normally you're like, oh, it's getting hot, it's exo. Like most people just say warmer things releasing energy. No, no, no. I'm transferring from the surroundings to the system. So that means that this is accepting energy or absorbing energy, which is going to be me warming up your cold beverage. And that would be an endothermic process. Okay, so energy of the universe is constant. Flow between the two is conserved. It's just one is endo and one is exo. You guys good there? I've shown this equation like 3 times now. Oh, the only thing I haven't really related this to is Q. Okay, so we've referenced Q equals MCAT, right? Turn to the person next to you, tell what each variable means, and the unit we should write for them. All right, Jillian, what is Q? Heat. CJ, what's the unit for heat? Joules. Fatima, what is M? Mass, what's the unit for mass? William. Grams. Drew, what is, oh, hold on. Drew read kinetics, guys. Okay. So, Emily, what is C? Specific heat capacity. Specific heat capacity. So the word capacity is kind of what we're representing the C with. So specific heat is what we generally refer to it as, but it's definitely specific heat capacity, which is how we get the C involved. What are the units for that, Chase? For C. It's the complex one. It's got joules in it. Joules divided by grams. Good job, Chase. You're like ventriloquist. Okay. And temperature, everybody. Whoa, I heard Kelvin. Whoa. It is Celsius and temperature. I mean, Celsius and thermochemistry. Kelvin we use in gases. Okay. I know, we've been dealing with Kelvin for a while. So I'll explain my gibberish. Okay. So temperature is in Celsius when we're dealing with heat. But when we're dealing with thermodynamics, which happens like a week from now, we'll then convert back to Kelvin. Sorry, it happens. Cassie, what can you not read?
Oh, I was just asking if
So specific heat capacity is joules per grams times degrees Celsius, yeah. Okay? Yeah. Because we have to measure the temperature of things, right? What do all of our thermometers always measure in? Say again? Celsius or Fahrenheit, right? But we use the F word, it's just Celsius. Okay? So we don't have Kelvin thermometers. All right. Oh, now we have a problem. Okay? So, look at number 1. What are we calculating? Change in what? Internal energy, which is symbolized by what? No. What is internal energy? Delta E. Ooh, okay, we're solving for delta E. For a system undergoing an endothermic process, what does that mean to you? So positive Q is what you're saying, right? Absorbing heat, and specifically how much heat? 15.6. So I know that Q, which is the heat energy absorbed, endothermic process is positive 15.6 kilojoules. And where 1.4 kilojoules of work is done on the system. What does this phrase right here mean to you? W is what? Well, W is positive or negative? Positive, because work is done on the system, right? So W is equal to positive 1.4 kilojoules. Okay, what's the equation for delta E? Q plus W, right? So plug it in. 15.6 kilojoules plus 1.4, please not use a calculator. 17.0, because we have to deal with our sig figs. So delta E, 17.0. Why do I have to have a decimal here? So in terms of addition and subtraction, I don't count sig figs like I traditionally do. What do I count instead? Decimal points, right? So how many decimals are in the first one? 1 decimal. How many decimals in the second one? 1 decimal. So the weakest link is just 1 decimal, so therefore I record to 1 decimal. If it were 15.6 plus 2, I'd record to how many decimals? 0 decimals, so just the number itself. Okay, moving on. Easy peasy, right? It's just the perspective stuff. Here's another one. Go ahead and do it now. Here's the person next to you. I was looking at it. All right, what is your Q? Negative 125 kilojoules, right? So it says released energy, so it's exothermic negative. What's your W? So work's still done on the system, so you're adding it to yourself, 104 kilojoules, and what do we get? Negative 21 kilojoules. Notice there's no decimal points, so therefore we just regard it as just an integer here. Okay, keep going. Write down your givens. I will help you here, but get started without me. I keep hearing moles. Yes, I didn't mean to write moles here. This is called molar heat capacity versus specific heat capacity. Works the same way, but what do you notice I have here? So what I have to do with this? Okay, make sure you do that. Keep going. I would just use the molar heat capacity as moles and then keep your.
So this, what is the specific capacity? Is that just
How many moles is this container? I'm not going to calculate anything. How many moles is that? 78. What's y'all's volume change? So did you do V final minus V initial? So what's V final? 1840 liters. And that dot means there's 4 sig figs, right? Subtract what? 1910. So I heard, let me put a dot right there. Meters. I heard 70. What'd you say? Negative 70. Okay, cool. Negative 70 liters. Okay. I have moles and I have negative 70 liters. What else do I have? I have temperature as 15 degrees Celsius. Now, do I need to change this to Kelvin? No, just by chance. It decreased by that. So what do I write here instead? Negative 15. So it decreased by 15 degrees Celsius. What else do I have? P is 1 atmosphere, right? Yeah, that's 1 atmosphere. There you go. And then molar heat capacity, C is equal to 20.8 joules per mole degrees Celsius. Okay, what do you guys want to solve for first? Q, okay, so here we go. Q is equal to what? Mass times specific heat capacity times delta T, or I could conclude this as moles times the molar heat capacity times C, okay, or delta T. So that's what? Moles, which is what? 78.25 moles times what? 20.8 joules divided by moles degrees Celsius, and then my temperature is, which is what? Okay, so what units cancel? Moles and Celsius, which makes sense. I need joules, right? So what's our Q in joules? Negative, right? Negative 24,414 joules. Okay, I'm not rounding this yet to sig figs. I want my whole answer just to not have rounding here. How do you get work? Negative. So work is equal to negative P times delta V. What's our P? Negative. So negative 1 atmosphere times what? Negative 70 liters. So what is this? 70 ATM liters, right? Doesn't make any sense. So this is where I said I have to show you the conversion to get from pressure volume units to joules. The conversion is 1 atmosphere liter, so 1 times atmosphere liters is equal to 101.3 joules. Does that number look familiar? Right, it's related through the Pascal. Joules are related to Pascals, so that's how we interpret this unit. Okay, so now take your atmosphere liters and convert to joules. So what do you need to do? multiply, right? 70 atmosphere liters times 1 atmosphere liter on the bottom, 101.3 joules gives us what? 7,091, yeah, joules. Right, so this is W. Now, how do I get internal energy? Just add them up, right? What's my Q? Negative 24,414 joules. What's my W? 7,091 joules. And can we just verify, how does this make sense that the W is, or the work is positive? What did it say about the, was this an expansion problem or a compression problem? The volume went from what to what? It went down, right? So it compressed. So the system did gain that energy, which is why it's positive. Sometimes you need to rationalize that as you go. So then this is going to be negative what? 17 what? 323 joules. Can we convert this to kilojoules? How many sig figs do I need? So I subtracted my volume, so there's only how many in volume? 2, so 70 points. So there's 2 sig figs. Those technically should be to what? 2. So what is this to 2 sig figs in kilojoules? Negative 17 kilojoules. Okay, and that's our total energy. Okay, how do you feel about working energy? Not bad, it's just, one equation. You just have to, okay, one equation brings them together, but 2 equations work together. All right, so there's one last thing I need to tell you. It's the conversion between joules and calories. Who's ever heard of calorie? Everybody, right? And I've shared my fun fact with everybody at one point in time during my class, but who has food? Oh, okay, so this probably doesn't have any on it. Does anyone have food with a label on it? Like a nutrition label. Kind of strong here, kind of strong. Yeah, Cracker Patch. Okay, so. Oh, sorry. Were you trying to give that to me? Mold. Okay, so I'm using the cream cheese and chives. This package has 190 calories per serving. I don't know if you ever noticed, but the capital C calorie on your nutrition labels, it's now lowercase c calorie. You notice on my board it's lowercase c calorie? Yes? Yes? Okay, so we're going to convert her big C calories to joules. Okay? So 190 calorie big C calorie is actually equal to 190 kilocalorie. So big C calorie is equal to a kilocalorie. They don't believe that we're smart enough to interpret what this means in the United States, so they just lied to us and say big C calorie without us really noticing. So if 190 calorie big C calories is equal to kilocalories, I want you guys to convert this to little c calories. Kilocalories to little c calories. What's the difference between kilo and base? 1,000, so we're up at 1,000. On the top, so 1,000 little c calories is equivalent to 1 kilocalorie. Okay, so Jillian, how many calories are in that pack? 190,000 calories in that little pack of crackers. Okay, so what's your normal calorie limit a day if you're an active adolescent? 2,000, 2,500, right? So they are actually saying that your limit daily is 2,000 to 3,000. It kind of depends on how active you are. Big C calories, which is how many true calories? 2 million calories a day. All right, so that's your limit, guys. Just 2 million calories a day. Like, take it easy. I just gave you some candy. But that's because most people can't rationalize, like, what their packages, their nutrition labels are telling them. So they don't tell us this lovely information. The FDA doesn't think we're smart enough. But we are. But regardless, you can convert this to calories and joules, okay? All right, so pull out the packet. Pull the packet. Let's take a couple minutes on energy first. So it's the first problem set on your big packet. First problem set. And I think I can start, yeah. Start with the star ones, the asterisk ones, okay? Start with the asterisk ones. So 1, 3, 6, 8, 10, 11. 1, 3, 6, 8, 10, 11. So just start on a couple for now, and then we'll see how much more practice we really need. Okay. We did one. We did one. Score. And did we do two? No, we didn't. DE means delta. Deltas are hard to put in Comic Sans. I know. It's a struggle. But so DE means delta energy.
It looks like it's a person. It looks like a person.
Oh my God, isn't it strange? That's like a... Whatever the symbol is there, it's not one of those 60 delta. Not like a little, somebody doing yoga. I'll see what kind of music I can inspire you with.